Hello everyone, welcome to my channel. In this video, I'll talk about the Bernoulli distribution. For this, one must be clear with the concepts of the probability mass function and the discrete random variable. I already made the videos based on these specific topics. So if you are not clear with these concepts, I suggest you to first go and watch these videos based on these topics and then come back for this video. You can find the link for these videos in the description box. I'll put the link in the description box. Now let's begin with the Bernoulli distribution. Here we have a brief outline of this video. I shall start with the basic understanding of the Bernoulli distribution and then few examples based on this Bernoulli distribution. Then I'll talk about the probability mass function and how to compute the expected value and the variance of the Bernoulli distribution by definition. Then the moment generating function and how to compute the expected value and variance with the help of this moment generating function. So in this video, we'll compute expected value and variance by both ways, that is by definition of the expected value as well as with the help of the moment generating function. Okay, so now coming to this Bernoulli distribution, first point that Bernoulli distribution, it is a discrete probability distribution. That means if x is a Bernoulli's random variable, so it is taking only distinct values to discrete values, and for a Bernoulli's random variable, this capital X, it can take only two values, x is equals to 0 and x is equals to 1. So that means for a Bernoulli distribution, the random variable, it will take two values 0 and 1. Secondly, for a Bernoulli distribution, there is a single trial. That means whenever we are performing an experiment a single time, flipping a coin single time, or rolling a dice single time. So that means it is a case of a Bernoulli distribution. If we are performing something a single time, so a single trial is there in the Bernoulli distribution. And the third one, that this trial results in only two outcomes, either a success or a failure. That means if we have a success, then the Bernoulli's random variable, it will take value 1. If we have a failure, then it will take value 0. So that means in the Bernoulli's distribution, we have a single trial, and this trial, it results in only two outcomes, success or failure. If there is a success, then the Bernoulli's random variable will take value x is equals to 1. If there is a failure, then the Bernoulli's random variable will take value x is equals to 0. Where the probability of success, it is given by small p, and the probability of failure, it is given by small q. And what is q? Q, it is nothing but 1 minus p, such that probability of success plus probability of failure, it is equals to 1. So whenever there is a single trial and that trial results in only two outcomes, success and failure, if it is a success, then the Bernoulli's random variable takes x is equals to 1. If it is a failure, then the Bernoulli's random variable takes x is equals to 0, where the probability of success, it is given by small p, and the probability of failure, it is given by small q, such that p plus q, it is equals to 1. So this type of trial, that is a single trial having only two outcomes, success and failure, it is known as the Bernoulli's trial. So this type of questions where we have a single trial and that trial results in only two outcomes, this can be answered with the help of this Bernoulli distribution. Now consider an example based on the Bernoulli distribution. So consider an example of flipping a coin a single time. So when we flip a coin and if we want a head, so that means getting a head, it is a success for us, and getting a tail, it is a failure. So that means flipping a coin a single time, getting a head, this is a success, and getting a tail, it is a failure. Single time we are flipping a coin, so it is a case of a Bernoulli distribution, and here we have only two outcomes, either a success or a failure. Similarly, if we are taking other example, that is rolling a dice. So rolling a dice single time and getting a 6, it is a success. So getting a 6, it is a success, and getting any other number, it is a failure. So what is the probability of getting a 6? So this type of question we can answer with the help of the Bernoulli distribution. So getting a 6, it is a success, getting a any other number, it is a failure. So that means we have a single trial, and here we have only two outcomes: success if we are getting a 6, failure if we are getting any other number. Or in the same experiment we can say that getting an even number. So if we are getting 2 4 6, this is a success, and if we are getting an odd number, that is 1 3 5, then it is a failure. So when we roll a dice single time, what is the probability of getting an even number? So this is a question based on the Bernoulli distribution. Probability mass function of the Bernoulli distribution. Now probability mass function, it is given by fx of x, where this capital X, it is denoting the that x is a Bernoulli random variable, and this small x, it is the capital X, the values that it is taking. So for a Bernoulli random variable, x will take only two values. X is equals to 0 when in a single trial there is a failure, and x is equals to 1 when in a single trial there is a success. And the probability of success, it is given by small p, and the probability of failure, it is given by small q, or we can simply write it as 1 minus p. So now this fx of x, this is equals to p whenever we have a success, that is when x is taking value 1. So at x is equals to 1, we have a success, so that means it is p, and x is equals to 0, there is a failure, that means it is equals to q, or we can simply write this as q is equals to 1 minus p. So this is the probability mass function of the Bernoulli distribution. In the combined form, how can we write this one? That means here x is taking only two values, x is equals to 0 and 1, and this is equals to p to the power x and q to the power 1 minus x. So when we substitute x is equals to 0, so this becomes p to the power 0, which is 1, and q to the power 1 minus 0, which is simply q. So that means at x is equals to 0, it is q, and at x is equals to 1, this is small p. So this is the probability mass function of the Bernoulli distribution, that is fx of x. Note, for a Bernoulli's random variable, this capital X, it denotes the number of success in a single trial. So this is number of success in a single trial. So if it is taking value 0, that means 0 number of success, and if it is taking value 1, that means we have a success. So that means for a 0 we have a failure, for a 1 we have a success. So this X denotes the number of success in a single trial. Consider an example of flipping a coin single time. So if we want a head, so getting a head, it is a success. So what is the probability mass function here? So when we flip a coin single time, the probability of getting a head, this is equals to 1 by 2, and probability of getting a tail, it is equals to 1 by 2. So that means getting a head, it is a success, this is a success, and getting a tail, this is a failure. So this means fx of x, this is given by 0.5 if x is equals to 0, that means if we have a failure, it is 0.5, and 0.5 if x is equals to 1, that is at x is equals to 1, this is 0.5. Another example, rolling a dice. So getting a 6, it is a success, and getting any other number, it is a failure. So probability of getting 6, this is nothing but, because the total in a sample space, the total outcomes are 1 2 3 4 5 6. So getting a 6, this is a success, so probability of getting a 6, it is 1 by 6, and probability of getting any other number, this is nothing but 5 by 6. So this is, if we are getting 1 2 3 4 5, so the probability of getting any other number other than 6, so this is 5 by 6. And the probability mass function, that is fx of x, this is given by 1 by 6, because we have a success here whenever x is equals to 1, and 5 by 6 whenever we have a failure, that is x is equals to 0, or we are getting any other number. So this is the probability mass function when we roll a dice. Expectation and variance of the Bernoulli distribution. The probability mass function of the Bernoulli distribution, it is given by p to the power x and q to the power 1 minus x, where x is taking only two values, 0 and 1. So the expected value of x, by definition, it is given by, since x it is a discrete random variable, so we'll use summation here, and x is taking only two values, so it is going from 0 to 1. The function of x here, it is simply x, so this is x, and the probability mass function, it is fx of x. When we plug in x is equals to 0, so this becomes 0 times fx at 0 plus 1 times fx at 1. Now 0 times something, it is 0, plus 1 times fx at 1, that is, substitute x is equals to 1 in the probability mass function. So this simply becomes p to the power 1, it is p, and q to the power 1 minus 1, it is 0. So q to the power 0 is 1. So this is simply p. So this is the expected value of x. Now coming to, in order to compute the variance of x, we know that the formula for this, computational formula for this variance of x, this is expected value of x square minus expected value of x whole square. Now for this we need to compute expected value of x square. So what is expected value of x square? So this time the function of x is x square, so this becomes, again, x is, it is a discrete random variable, so we'll use summation, and x is taking only two values, 0 and 1, and the function here is x square, so write it x square, and the probability mass function. So when we plug in x is equals to 0, so 0 square times fx at 0, it is simply 0, plus 1 square, it is 1 times fx at 1, so this is simply fx at 1. So when we plug in x is equals to 1 in the probability mass function, it is again equals to p. Now what is variance of x? Substitute the values of x, expected value of x square and expected value of x. So expected value of x square, it is p, minus expected value of x whole square, that is p square. So this is nothing but p, and this is 1 minus p, which is equals to pq. So this is the variance for the Bernoulli distribution, and expected value of x, it is equals to p. Moment generating function of the Bernoulli distribution. Now, by definition of this moment generating function, this mx of t, this is given by expected value of e to the power tx. Now, this expected value, by definition, it is given by, since capital X, it is a discrete random variable, so we'll use summation here. The function of x, this is e to the power tx, so write this function as it is, e to the power tx, multiply by its probability mass function, and x is taking only two values for the Bernoulli distribution, that is 0 and 1. So when we substitute x is equals to 0, so again e to the power t multiplied by 0. So this becomes e to the power 0, which is 1, and this is fx at 0. Plus when we plug in x is equals to 1, so it becomes e to the power t times 1. So this is e to the power t fx at 1. And we know that the probability mass function of the Bernoulli distribution, it is p to the power x and q to the power 1 minus x. So this e to the power 0 is 1, and fx at 0, simply substitute x is equals to 0 in the probability mass function. So this is p to the power 0, which is 1, and q to the power 1 minus 0, it is simply q. So this is q plus e to the power t, and when we plug in x is equals to 1, this is coming out to be p. So this is the moment generating function, that is q plus p e to the power. Now expected value and variance with the help of the moment generating function. We know that the moment generating function of the Bernoulli distribution, it is given by q plus p e to the power t, where this small p denotes the probability of success and small q denotes the probability of failure. Now, in order to compute the expected value of x with the help of the moment generating function, since here x to the power 1, so we differentiate the moment generating function one time with respect to t, and then plug in t is equals to 0. So this becomes d by dt, and the moment generating function, it is q plus p e to the power t, and then plug in t is equals to 0. So the differentiation of this moment generating function with respect to t. When we differentiate q with respect to t, it is 0, and when we differentiate p to the power t with respect to t, this is simply p to the power t, and then plug in t is equals to 0. So when we substitute t is equals to 0, it is simply small p, that is expected value of x, it is nothing but simply p. So this is the moment expected value using the moment generating function. Now in order to compute expected value of x square, so here we have x to the power 2, so that means here we are going to differentiate twice the moment generating function with respect to t, and then plug in t is equals to 0. And we know the one time differentiation of the moment generating function, it is nothing but p to the power t, so I'm simply using this here. So this is p to the power t, and then plug in t is equals to 0. Again, if we differentiate p to the power t with respect to t, so this is simply p to the power t, and then plug in t is equals to 0, so which is again equals to p. So that means expected value of x square, it is also equals to p. Now the variance of x, this is equals to expected value of x square minus expected value of x whole square. So this is equals to expected value of x square is p, so I am simply writing p here. Expected value of x, it is p, so p whole square is, this is p square. We can take p common, so this is p and this is 1 minus p. And what is 1 minus p? 1 minus p, it is nothing but q, so this is simply pq. So variance of x, it is pq. So the expected value of x for the Bernoulli distribution, it is p. Variance of x, this is pq, and moment generating function of the Bernoulli distribution, it is given by q plus p e to the power t. This is all about the Bernoulli distribution. I hope you liked this video. If you did like this video, please don't forget to hit like and subscribe to my channel. Also, if you have any queries related to any mathematics concept, you can mail me your queries at my email ID. You can find my email ID in the description box. Thank you everyone.